So when I talk about periodic trends, that's being able to look at a periodic table, and you should be able to have information immediately based on locations of elements. It's not about having a reference sheet. It's not about having numbers and data. You should be able to say, hey, this atom's bigger, this atom's smaller, this element is going to lose an electron faster, this one's not going to lose an electron. That's where you need to kind of be able to live when you look at a periodic table. Suggestion as we go, if you don't have your orange periodic tables, that would be good to have them on the side so you don't have to go back and forth. If you want to grab those about halfway through, you're going to need them. So if I quickly just look at each of these, and again, I've already typed them for you. Atomic radius. So that is half the distance between two nuclei of two like atoms. The reason why that's the case is that atoms have electron clouds as their outer barrier size. So what you can't do is you can't measure it from the actual outside of it. So what you have to do is measure it from one nucleus or nuclei to the other. So the nucleus of one to the nucleus of the other. And then you just take half that distance. And the reason why, again, is that the nucleus is the only solid part of that atom. Okay? A good way to remember, and we'll talk about it, but as you move down the table, you're gaining energy levels, right? The atom's getting bigger and bigger and bigger. As you move across, you are actually gaining nuclear charge. So that's actually one thing I wanted to write in here. So as you're going to the right, it's a very important word, nuclear charge. You're gaining this. You learned this in first year chem, but it probably didn't mean a lot to you yet. So here you're gaining nuclear charge. Here you're gaining energy levels. I'm only going to talk about the atomic radius in this depth because the radius is everything. If you understand the size of your atom, you can actually explain a lot. So as I move down, the reason why it gets bigger is because I'm gaining energy levels. The reason why it's getting smaller moving across, because the nucleus is getting bigger and it's sucking in those electrons. It's that simple. How do you remember what this is? We learned this last year. If you don't remember, that's okay. You can kind of remember the trends by looking at a snowman. And that was a horrible looking snowman. But it gets larger going down and smaller going to the right. So you can think of snowman. Okay? So it is so important. We are never going to say, why can't you remove an electron from element X or element Y? And your response is, it doesn't want to lose electrons. It doesn't want a pony for its birthday. It doesn't want a car for its 16th birthday. It doesn't want anything for Christmas or Hanukkah. It is not a person. It is all about the attraction and the distance of the nucleus to an electron eventually. And that's what I have to kind of get you to be at, okay? So we'll get there in a moment, okay? So that's atomic radius. Shielding effect, I'll just leave it on the screen there. There's not much to it. This helps explain other things. So what does a shield do? It blocks it blocks an item from some other thing that's occurring. So if it's you versus an arrow or whatever. So it's the reduction of the traction of the nucleus to the to the outer atoms. That should be outer. Although I love otters at the zoo. They are adorable. Oh boy. Due to the shielding of the inner electrons. The otter electrons. That's great. So it's the shield's between the nucleus and the outer electrons, and the shield is those inner electrons. So if you have a lot of electrons in the middle, it's going to cause a reduction of the attraction from the nucleus to the outer electrons. Okay? Again, I'm not acting like you have this all memorized. I'm just trying to go through this so we can address the new items that I want to look at today. Ionization energy. Energy associated with removing an electron. This, I think, is important to make sure you're understanding. It's the energy. I'm going to actually highlight it in a different color. So what that means is if it's increasing, it's actually more difficult. So it's more difficult to remove, or it's easier to remove. Well, why? Nuclear charge. Over here, bigger nucleus. So nuclear charge here, bigger atoms, further distance. And I'll explain it more and more, but the electrons are further away, so it's easier to remove. The attraction, it's all gonna be, you know what? I'm gonna write it right up here. Bear with me, I'm trying to think of things that are going to help you later. So, factors that are going to screw around either making that attraction between the nucleus and the outer electron greater or weaker. The distance, if it's close, more attraction. Further away, worse, right? Nuclear charge, bigger nucleus, might be able to hold on the electrons easier. Smaller nucleus, maybe not. And then shielding, is there junk in the middle between that nucleus and that outer atom? So those are some of the factors. I'm trying to give you some ammunition because this is going to be free response questions, and we don't want to fall short on not being able to just hit the item that we want to say. And this is kind of tricky because you've learned this stuff, but you haven't learned it at the level that you probably need to yet. Okay? So again, we're going to practice all this today. Last two things. Electron affinity, this is about adding electrons. This is, geez, a lot of autocorrect. That was adding an electron. A lot of adding an electron. So the reason why you can add an electron easier in the upper right is because it's smaller. I'll write that. Smaller and greater nuclear charge. So that's why it's easier. Opposite. The other one, they're bigger, and the nuclear charge, actually, that you can't say about the nuclear charge. The nuclear charge is actually bigger down there, but as you move across, it gets larger on any one row. So the problem is why it's larger here, the nuclear charge, but you gained an energy level. So I could write that, greater energy levels. Okay, so again, that makes it harder for an electron to be gained when it's really far away. It's further from the nucleus, so the nucleus can't grab onto it as easily. And then finally, electronegativity is a very similar idea. It's just, it's pulling electrons when bonded, okay? So we've talked about that. We'll look at that next chapter about shapes and polarity, and when you're bonded, can one element steal another element or electron from it? Okay. So I have a bunch of images. I don't want you to be overwhelmed with that. I was just showing you some stuff. So here's the picture of the nucleus. Shielding effect is the idea of all of this is the shield, right? So here's my outer atom. My outer electron, sorry, and then all of this is my shield. Okay, so the more in there, the more I'm going to block that attraction between the nucleus and the outer electron. That's shielding effect. You can see atomic radius. Here's just some visuals. A lot of you are very visual people, so I just wanted to show it. See how it's so big down here and it's so tiny up there. Ionization energy, the exact opposite. It gets larger going to the upper right. Again, just some good visual stuff. Which leads me to my main event today, or one of my two main events. So, well, sorry, I got ahead of myself. I forgot about this page. This is ionization energy. Please highlight this. I know this is a heavier Friday than maybe you're hoping, but the sooner I get this to you, it can marinate and it will help you more later. So what these are showing you guys is the peaks. The higher it is, the harder it is to remove, okay? So these are all, hopefully you can kind of do this with me. Difficult to remove electron. And these are easy to remove, or easier. So I hope that you see that these are all noble gases on the top. And these down here are alkali metals. And eventually you're going to actually have to explain why. It is not, noble gases don't want to give up an electron. It's because they are the smallest on their row. And then we'll talk about it later. I don't want to jumble this part of the sheet up too much, but it's never about want. The minute you say want, you're going to be torched on that. Here, alkali metals, you have a lot of shielding. You just gained an energy level. You gained one energy level. So that one electron's sitting way out there with extra shielding. And again, we'll discuss all that. With that, this is something we'll talk later. I'll just highlight this for now. Successive ionization energies, it's showing every time I remove an electron. So I remove the first electron, I remove the second one. It gets harder every single time you remove an electron. And there's a point where it gets really difficult. So highlight this word, core electrons. There's outer electrons and there's inner or core electrons. Core electrons are not valence electrons. So outer electrons are what we call valence electrons. So it's easy to remove, easier to remove valence electrons. All right, that is the last part of my electrons. There's just one more vocab word I have to give you. It's an important one, and again, throwing it out there now. We will discuss it more later. It's isoelectronic. Please make sure that you see it, you highlight it, whatever you need to do. And what that just means is they all have the same number of electrons. And I know I'm giving you a lot, but it's leading into what I need to get to you today. So you'll see what's the difference. The nucleus is different. So look at, like this has O2 minus, F minus, Ne, Na plus, Mg2 plus. So they're all related to kind of what we would know an atom does to become an ion, right? Oh, this is right next to neon on the periodic table. It gained one. It gained 2 electrons. Oh, this one lost an electron. This one lost 2 electrons. So they're all trying to, quote unquote, look like neon. This was before, and then they're gaining them. So they're all going to have that same electron configuration, and that's important. They're going to have the same, in fact, I'm going to highlight that. If I were you, I'd want to see that right there. They're all going to have that, which I know it's also down here. Oh, I already had written it. Look at me. I'm giving you all sorts of great notes, and I'm not even maximizing it. Okay, let's see. Yes, I am there. Okay, so in first year chem, we've talked about radius. We've talked about ionization energy. Unfortunately, I probably didn't feel like we applied it as much. You are going to feel like superstars with this stuff because you're going to have just a better understanding. So there are 4 instances that I have here. And these are extremely important. If you have your periodic table, it's important to kind of see that. So any free response, and I'm going to have us do some in about 10 minutes. I'm going to break you up, and you're all just going to work on one question. That's it. They're going to relate to these kinds of questions. Can you explain a situation? You don't have to have them memorized necessarily, but if they tell you a situation, can you digest it and then analyze what's going on? So for example, this first one, N versus O. And you may not want to write on yours, you may. I don't know. I just want to show you here. So N and O. So here's N, here's O. Notice that the trend changes. If we say ionization energy as you go to the right, sorry, I'll come back in a second. As you go this way, it gets bigger. So no matter what, if I go across, it should also be getting bigger. But if you notice, it looks like a stock market ticker, is that it's changing. It doesn't go straight up. It actually goes up, and then it actually drops, then it goes up, back up. So the question would be, justify why nitrogen has a greater ionization energy, translation. It's more difficult to remove an electron, a valence electron, than oxygen. And you'd be like, I don't know. So first, analyze what you know. I always write down, if I'm doing a chemical reaction, I write down the reaction. If I'm doing some math, I organize my information. Here I'm talking about electrons, so why not organize my electrons? So the ending of nitrogen looks like that, versus oxygen, which looks like that. Okay, that's just a fact. I'm not having any kind of opinion in here yet. I'm just saying this is the difference between the endings of my electron configurations or orbital diagrams. So now what you have to explain, and I already have written it here, why is this greater? Why is that more difficult to remove electron? So it's more difficult to remove that electron than that electron. That's what it's basically saying. Okay? I think this one's really hard. So if you look at it, they'd be like, I don't know. Here's the wrong answer. Well, the nitrogen is all filled one time, so it doesn't want to give away its electron because it wants to stay balanced. Balanced, want, doesn't exist. Nature doesn't know anything like that. All your job is to understand forces, and forces are related to distances, charges, strengthening and weakening those forces, okay? So here is your answer. I would open this up, but this one, and if you did figure this out, fantastic. But this one I think is really difficult. Because of that single pairing of electrons, there is a natural repulsion. I'm going to underline that and highlight it. I'm giving you the keys to the kingdom here on every one of these problems. Natural repulsion between the paired electrons in oxygen, whereas nitrogen has all unpaired electrons. If you just drop natural repulsion and even say something coherently without saying the word want, you're probably going to get it. And I'm not reading off anything. I'm just going off. So every time I write this, it might sound a little differently. But there's a natural repulsion between the paired electrons in oxygen, whereas nitrogen has all unpaired electrons. And then you could, if it already had said if it's more difficult, if it didn't say, if you had to say which one is more difficult, then you would have said which makes it easier to remove it from oxygen or more difficult to remove it from nitrogen. Okay? But notice that I said something about both. You have to say something about both usually. Okay? So that's scenario one. We only have 4 scenarios today. Please ask questions as we go. I already wrote the greater, and it's not a secret. You can read a chart. So this one's greater. Let's find out why. So here's my second scenario. BE and B. So it jumps up to BE, then back down to B. Why is that more difficult to remove in BE than in B? Well, let's take a look. BE, oops, get too close. Looks like this. I gotta write this smaller. I'll write it at the end. B looks like this. I need to shrink this. Here, I'm going to put that up there. So it's saying that BE is greater. So what I'm trying to do, I'm even going to highlight the electron that we're trying to remove. It's the last placed electron, you guys. It's the last one. It's the outermost electron always. That's the one I'm trying to remove. So why is that one most difficult to remove? Well, this is why in here. This electron is further from the nucleus. Every time I add even a sublevel, it's further away. Plus, there is shielding occurring. So the nucleus here, you guys, if I just drew it all out, you don't have to draw it all out. But if I have it like this, it looks like that with a nuclear charge of 4. This one has a nuclear charge of 5. And this is why you'd argue, wait a minute, wouldn't 5 hold it in tighter? That's the problem. This is why it's a hard problem. Is that this charge here only has to reach to that electron, while this charge, even though it's 5, has to reach all the way through this to get all the way up to here. So the distance is greater, and there's more shielding on that one. So let me write that out. Wow, I don't want to get wordy here. I get wordy really fast in these. Oh, shoot. I'm sorry. This is the longest one. Wow. Okay. The electron in boron is located in the 2p, whereas the electron in Be is in 2s. Again, you might be able to shorten that part up. There is a greater distance, so I'm going to highlight a couple words here. There's a greater distance between the boron's 2p electron and additional shielding, which makes it easier to remove. Those are the things I want to get across. Again, am I writing poetry here? No. Am I saying the greatest example every time? No. I might write this better one day than the other, but what I'm trying to do is hit the things that I'm highlighting, okay? I got to be able to work that in. So I look at that problem going, oh, well, it's greater distance and there's more shielding. What I couldn't talk about was the nuclear charge, the charge of the nucleus. If I actually said that this has 5 and this has 4, well, 5, if I talk about the nucleus, shouldn't it be holding on the electrons harder because it had a bigger nuclear charge? But it's not holding on it tighter. So don't bring up something that goes against your argument. Okay, you can't bring it up then. Oh, I want to talk about the size, but does the size help or hurt? So you got to make sure you're talking about it in the right way. All right, 2 more. Again, I'm only going to have you practice 1 of these once we get finished with this. So zinc versus gallium. So zinc, let me do a whole different highlighted color. I got to find it. There you are. Zinc. I think gallium's right here. Yeah. Wait. Yes. It's the next one. We probably need to write that in. Oops. All right. So we'll try to shorten this up a little bit. but zinc's greater, so I'm going to kind of write it above. I don't want to lose space here. So my zinc, if you look at this one, zinc is at the ending of the d orbital. So it's totally full. Gallium is the next element, so it looks like this. So it might not ask just specifically why it's less or more, but maybe why it's such a huge drop. Like that's a pretty big drop in between, and I hope you're already seeing it. So I'm going to highlight the electron that I'm trying to get rid of. Is that, let me, if you're like, wait, I see it now from the last question. It's totally the same question, but this one, if you wanted to specifically say it, check this out if you're still writing, is that this right here, zinc, this electron doesn't benefit from all of these 9 electrons, they don't get the benefit of that shield. So they're not blocking the nucleus at all. By adding one more sublevel, that electron gains all 10 extra electrons of a shield, which is a huge reduction of an attraction of my nucleus to the outer. I got to go through all of that stuff to get to it. So basically put, the gallium has a much greater shielding. Let's pretend I already placed, or I drew that in my problem, and I said, like, you know, using the items above. I say the gallium has I'm not writing as well. I get wordy really fast on these because there's a lot of things I'd like to say. I don't want to miss them. So larger shield and further from the nucleus. Every time. Have I said want once? No. Have I said anything about something being full and that's why it's harder to remove? No. It's about distance, it's about shielding, and it will be about potentially the nucleus. But again, none of these I could talk about the nucleus yet. All right, final one. I think this one's actually the one that would make sense if I asked you all four. I have a lot of faith and confidence in you guys, but of all 4 of these, I think you would have actually gotten this one right off the bat. So AR versus K. So I'm just trying to find a new color here. There's AR, there's K, and AR is the greater one. So now this one's a little tricky. This is number 18. This is number 19. I shouldn't say tricky, but let's just say where it ends in. So the valence electrons here are 3s2, 3p6, whereas this is 4s1. Oh, okay. So can I talk about nuclear charge? No, because the nuclear charge would hold electrons tighter, and they aren't. So what you're saying on this one, it's pretty straightforward, is that K has an additional energy level. Wow, I'm writing energy twice. You're writing the same things every time. Yeah, right now I am. The thing is, you have to say the scenarios. So in here, maybe I can just write it here and then I can talk about it. You might need to work them into the problem, but you do need to address it. You need to say something. So again, I don't feel great about the fact that, okay, that I didn't give you anything really new here. If you want to be specific, you can say additional energy level being in the 4th versus the 3rd. And then further from the nucleus with it. There's a lot of good stuff in that one though, because it's repetitive. So, that being said, every year there are questions about what I just showed you, and I have them right here. So I'm going to read them out loud once, and I'm going to try to show both things in case you're still writing. It says, explain the following observations using principles of atomic structure and or bonding. So that's what we're doing right now. A, potassium has a lower first ionization energy than lithium. B, the atomic radius of N3- is larger than that of O2-. C, a calcium atom is larger than a zinc atom. Or D, a boron has a lower first ionization energy than beryllium, which I just did. So we're going to do the first 3.